This is part 2 of homework 3. So last time we went over different truss structures, monocoque structures, and semi-monocoque structures. And this time we are comparing different aircrafts that we found on the internet, and we classified it based on truss, monocoque, semi-monocoque structures. We looked at the skin thickness, wingspan, gross weight, and then with this information, we ended up plotting it via an Excel spreadsheet. So there are some clusters that are forming. Like over here, you can see that with around skin thickness of like 1 millimeter or less than 1, like in between 1 millimeter and 0.5 millimeters, sometimes like the wingspan is around 30 meters, which is a pretty large plane, right? Or within that same area, the wingspan could be smaller as well, at around 10 meters. So that is one pattern that I see. If anyone wants to add anything. And
to add, and also not just about the clusters, but maybe the outlying points also.
yeah.
What could be the reasons for the outliers, and you'd like to speculate?
Part of the reason for some of the outliers might have been due to the reliability of the data. It was hard to find like skin thicknesses for certain planes, especially for the truss wings. But yeah, that's probably one factor of the outliers. Does anyone else want to comment?
But what about you found, what were the sources?
Yeah, like some of the resources that I personally found.
Oh no, well, I was just going to say that similar to what Patrick said, the reason for so many outliers is that there wasn't a lot of data available, and so we kind of had to nitpick. Like there's one semi-monocoque outlier up there that has very sizable skin thickness, and so that wasn't really consistent with what we found overall with the semi-monocoque. And then the monocoque was kind of all over the place.
Another reason for some of the outliers is that our data didn't take into account the type of material that was used. It just looked at the basic wingspan and skin thickness, but if it's a stronger material, then you would need less of the material to cover it. So that's one of the things that we didn't really account for in this data.
I just thought about it, but we also didn't take into account whether the plane was for military purposes or civilian purposes. So like for military planes, you might have a thicker skin, just because it might take more damage than a civilian aircraft.
Yeah, and also, like, I feel like maybe if we had, like, more data points that we went through, like, maybe, like, a clear, sort of, like, pattern might emerge, but within, like, the 10, 15 data points that we do have, most of these guys are tending towards here. And within these guys, these tend to be semi-monocoque, and a lot of our data points that we found were semi-monocoque designs. And the one truss aircraft that we have had a particularly large skin thickness, and that could just be because of the materials it was made out of, also when it was made, because it was a pretty old airplane, right? So, so this was like early 1900s, so that's why. But yeah, like a lot of the more recent ones definitely seem to have thinner skin thickness. And then over here, it seems like most of our gross weight for our airplanes, we're tending to be more towards the lower end comparatively. around like underneath 500, 50,000 kg. There seems to be a cluster both over here at around that one, like between 0.5 and 1 millimeter skin thickness, as well as in between this range between 1.5 and 2.5 millimeters as well.
You just jog my memory on the two monocoque aircraft. What are they?
Let's see. So monocoque aircraft are the three over here. So we have the de Havilland.
Still not sure what the Dreamliner.
It's one of the next slides.
Okay, we'll come to that. Sure.
I think I also
So
sort
those
of,
two
yeah.
points are probably the Comet and the Falcon.
Yeah.
What we have in orange.
Yeah, the de Havilland, the wingspan's pretty large, as well as, the Dreamliner definitely has like a higher gross weight than all of them, so that might be the outlier that we're seeing over here. Yeah.
Oh yeah.
Yeah. So that might be the de Havilland and the Falcon. So, y'all want to add comments? Yeah.
Okay. Here is the proof that the Dreamliner is monocoque. I found a couple different articles online, and the first one is from Monroe Aerospace, and it refers to the Dreamliner as monocoque, one because it has a frame, and the way the frame is structured is that of a monocoque airplane. So the main difference there's a couple different factors, but the main difference for categorization is whether it has stringers going along inside, so extra strings along the shell to reinforce it, which the Dreamliner does not, which makes it a monocoque aircraft. And here's another one at the bottom from the Science Direct article, and it says that it doesn't have additional stringers, but the way that the panels are laid out is that it doesn't really need it. It's sort of as if it is built in already, but it's not the stringers that they are referring to when they classify monocoque versus semi-monocoque. This is different. So and we can go back to the other slide before about the gross weight and see that the 787 is an outlier with gross weight at least. So the skin thickness is around the medium range, but the weight is a lot more than the other aircrafts. And I think the reason that they went with a monocoque design is that they weren't too concerned about weight, as it seems. They weren't trying to minimize weight to get it in parameters of the other aircraft, just because it's so large. I think they were more going for structural soundness as opposed to minimizing weight by choosing a monocoque design.
So those were important points that you guys brought out, and many of the things that you said are valid, because it's kind of a lot of speculation involved over here, because as you would have seen, it's very difficult to get this kind of data in the first place, and to a large extent we are probably comparing apples and oranges. Patrick brought out the important point about the differences between military and civilian aircraft, and within that also various categories that are possible. So also we are looking at the issue of going from monocoque to semi-monocoque when either the aircraft becomes large and or fast. So we are looking at it one at a time here. In terms of large, we are looking at it purely from a weight point of view or purely from a span point of view. May not always be the case, because there could be certain aircraft which are very high aspect ratio aircraft which might not be very heavy aircraft actually overall, so or may not be taking much loads either. So it's important to look at it from a more holistic perspective, which is kind of difficult with the limited amount of data we have, which is why we try to have a cursory look. But I think the message is quite clear in terms of the clusters, which Nilesh very clearly explained, and also in terms of I think the outlying points, what the reasons could be. I think Alexandra kind of speculated on that, especially with the Boeing 787. So let's continue with the topics that we were focusing on in the previous class. We were looking at three types of designs. I don't know what's happening with this. Just keep a watch on if the recording is going on. Yeah. Right. So as I said, we have three types of designs typically: the strength-based, stiffness-based, and stability-based. And more often than not, we will be considering at least two of these for most structural components. Quite a few of them will have all three considerations in place. And as I said, I would like to utilize the opportunity of talking about three types of design by introducing three types of material configurations as well. So in the previous one, we just looked at axial bar, which was kind of uniform in the thickness direction, whereas here we are looking at once again a beam-like structure but made out of a sandwich construction, so that you have thin face sheets on the top and the bottom which are quite stiff, and in between you have less stiff material, which could be a foam or it could be a honeycomb kind of a structure, metallic aluminum honeycomb for example. And these are very commonly used in aerospace engineering, because by having the larger stiffness materials farther away from the so-called center, which we will define more clearly as the neutral axis as we go forward, by having more of those stiffer materials on the top and the bottom, you're going to have a larger bending stiffness. Not only axial stiffness in terms of how much it deforms, how less it deforms for a given load, which is axial in direction, but also for the bending loads like what is indicated over here. And it's not that the material in between, which is a softer material like foam or even honeycomb, is useless. It also has a certain functionality, in the sense that there's also usually the bending moment doesn't come from a pure moment like this. It usually comes from a lift or a drag distribution along the span of the wing. So when that happens, what you typically have is not only bending moments but also transverse forces. So those transverse forces have to be resisted through transverse shearing stresses, and we will see how to calculate those as we go later on into the future classes. But those are typically taken mostly by the material in between. So in the sandwich structure, what we call as a sandwich configuration, the face sheets typically take the axial loads, compressive and tensile. So the direction in which the bending is shown over here, for example, it's clear that the top one will be stretched out, in other words it will be under tension, and the bottom will be pushed in, which means that it will be under compression. So the face sheets are very good at handling these normal stresses, either positive or negative, but The one in between is not good at that. Instead, it is good at handling the transverse shear which comes through the shearing stresses and strains. So typically the shearing stresses magnitude, maximum shearing stress is very small compared to the maximum bending stress that comes up. So usually it's not something like a design driver, but as far as the inner portion, which we call as core, the top and bottom are called as face sheets. The inner portion, irrespective of whether it's made of foam or it is made out of honeycomb, it's always called as the core. It's like a typical sandwich that you eat. You have all these stuffings in between, and on the top and the bottom you typically have bread. So essentially it is something like that. The bread is good at taking the axial loads, whereas the one in between is essentially good at taking the transverse shear. So the purpose, like in the previous case, the purpose, what was the driving force, what was the motivation? It was to delay the failure or to avoid the failure even if possible. So here on the other hand, we want to limit our deformations. So that's as far as the static way of looking at it is concerned. But we also saw that when we're talking about the various loading sources and the types of loads, we saw most of the aircraft components, structural components are loaded with dynamic loads, time varying loads, which means that the frequencies matter, the natural frequencies of these structural components. Based on their masses and their stiffnesses, they have certain natural frequencies at which if you try to force at that particular frequency, it will vibrate quite a bit, what we call as resonance, and it could be quite disastrous. So keeping that in mind, you try to push the design natural frequencies for various structural components as large as possible, so that the loads that are typically there are of lower frequency range, and you do not have an issue with they matching up with the natural frequency of the structural components, and therefore the possibility of resonance is kind of delayed. So the same kind of design changes that we make both in the choice of materials for these three layers and also their sizing in terms of what thickness of face sheets to have, what thickness of core to have, and how are they as a ratio of the length, width, etc. Those changes are going to affect both these aspects, the static loading response and the dynamic loading response. In static loading response, what are they going to do? They're going to help us have the deformations or deflections or rotations as low as possible, so that the original configuration is maintained pristine to the extent possible. But in dynamic loading situation, the same thing, apart from reducing the deformations, it also helps in avoiding resonance kind of situations, and therefore something kind of blowing up. So that's with the same decision, we are having two advantages from both a static and a dynamic perspective. So then if you look at this example, it's fixed at one end and it's free at the other, and the free end is where you're applying the load to keep things simple. But as I said, in the real situation, you'll typically have a distributed load, but nonetheless the effect is the same, that at each cross section you have a certain bending moment, just that in this case the bending moment is the same at any cross section you cut, whereas when you have a distribution, you will have very low bending moments here, and the bending moment will keep on increasing until it reaches the root, which is why you see that typically in an aircraft, a fixed wing aircraft, you would have the wings of much larger airfoils over here compared to the tip, which will be much smaller. The chord even might be quite small. In other words, there will be a taper in the wing shape. So you would have much smaller airfoil in terms of the thickness, as well as in terms of the length of the airfoil, which is the chord. You would have much smaller at the tip. Therefore, this is like a but here for simplicity we have shown a constant geometry cross section throughout. The breadth is B and the overall height is H, which is the total thickness of the two face sheets plus the core that you have. And the face sheets themselves, the top and the bottom, it is symmetric, both of thickness T each, and therefore those T's are typically very small compared to the overall thickness. So the overall thickness you have is H is made out of 2T, because there are two face sheets, top and bottom, plus the thickness of the core, which is approximately equal to h itself, because T is so small compared to h, right. So now the other aspect is also in terms of the core, that the very purpose is that you want to have a thick beam, but at the same time, if you're going to take the high quality material which offers a lot of stiffness and strength throughout the thickness, then you're going to have pay a penalty in terms of the density as well, because the density of these materials compared to foam density or honeycomb density is going to be very large, which means that the overall weight penalty is going to be large, which is why you do not fill it up entirely. The other reason is that the stresses are going to be larger at the outer edges, in this case on the top edge tension and the bottom edge compression, but it could reverse depending upon the flight conditions, but essentially you would have much larger stresses on the top and the bottom, and almost zero stresses as far as bending stresses are concerned in the center. So you might as well have a more flimsier material which is lighter in weight, which has a lower density, which is why honeycomb, which is mostly air space in between the walls of the honeycomb. So that is essentially what we are looking at. So the idea of having the core is, one, yes, it is also going to resist one kind of stress, which is the transverse shear stress, but in addition it also helps in identifying areas where the bending stress is small, and therefore you can reduce the mass, overall mass of the beam, and stiffness can still be guaranteed, because you are trying to push these stiffer materials farther away from the so-called center. They become even more capable of handling larger bending loads. So we will see why these geometric features matter a little later, but right now purely from the point of view of material selection, we want to identify a material parameter which is going to be of significance for a stiffness based design, whether it is static or dynamic. So that being the case, we will introduce first of all a geometric entity called the moment of inertia. So the moment of inertia is essentially a second moment of the inertia area, which you might have studied as part of certain maths courses before. But essentially what it is that about the center plane of this beam, what is the moment that the material above and below contributes. So here you have the face sheets which are of cross-sectional area breadth times the thickness. Each of them is of thickness T, the top sheet and the bottom sheet. So B times T gives you the cross-sectional area of one of the sheets. Similarly, the BT on the bottom is another which contributes. Therefore, you have two here. The factor 2 refers to there being two face sheets at equidistance. And what is the distance at which they are? Approximately, because of the fact that T is very small compared to H, it's at a distance of H by 2. From the mid plane, you see it's at a distance approximately H by 2 on the top and H by 2 on the bottom. Those are the face sheets. So the distance from the center squared times the cross-sectional area is what gives you the moment of inertia from a second moment point of view of the areas concerned. Okay, so we will get into more specifics of how to calculate this for various shapes, etc. later on. You might have been already exposed to some of these things from a dynamics perspective also when you took the dynamics course, but those are typically mass moments of inertia where the density comes in as well to give you a weighted average. Here it's purely a geometric property. There's no weightage of the density coming in. It's purely area times the distance of that area from the so-called center squared. And because there are two such face sheets, the factor 2 is over there. Okay. Now let's go just like what we did in the previous case, the strength based design. At the end of last class, we saw that it's like all other aerospace structures design, it is a weight sensitive design. So if it's a weight sensitive design, not only are we interested in its ability to handle the bending moments or certain dynamic conditions, what natural frequency it contributes, etc., but we are also interested in keeping it as low in weight as possible, which means that we are interested in looking at the mass as well. So now we look at the mass per unit span. the span is along what is marked as L over here, the length, half the span. So if you look at that, you see that it is the mass density rho, which is a material property, and therefore I have highlighted in blue. Unlike all the other quantities so far, T, H, B, etc., and even I for that matter, the moment of inertia, are all geometric properties. I have not highlighted them in blue. I am only highlighting the material property in blue over here. So it's the mass density times the cross-sectional area, which is B times T for each phase sheet, and there are two such phase sheets. So it becomes 2 rho Bt, and as I said, the core is typically of a much lighter material. So for a first cut approximation, you can ignore the weight of the core. It's only the weight of the phase sheets which matter. Not only are they stiffer, but they are heavier as well, and you can think of the mass per unit span as approximately 2 rho Bt. It will be slightly more than this because if you take the core into account, but that's not the purpose over here. Here the only purpose of this slide is to introduce a material property which will be the criteria for a stiffness based design. Like we got into one property already at the end of last class, which was sigma u, sigma subscript u divided by rho, which is the ultimate tensile strength divided by the density of that material. Similarly, we want to get some material property for the stiffness based design. That's what we are trying to head towards the end of the slide. Now we can do the same thing from both perspectives, from statics to dynamics, either statics or dynamics. Since I have already given you a flavor of statics with the strength based design, let me take a different turn over here and try to focus on the dynamics over here, so that we are exposed to certain flavors of everything. So natural frequencies for a finite degree of freedom system will be a finite number of natural frequencies. But here we have a continuous system because the material is continuous. The number of degrees of freedom of a continuous system like this is infinite. Unlike let's say if you have a simple pendulum, you have a 1 degree of freedom system. If you have a spring mass system including a damper or not, you would have a 1 degree of freedom system, etc. And with multiple masses connected by spring, etc., you can increase the number of degrees of freedom, but all of them will be examples where you have finite degrees of freedom. But when you have continuous material which is having a certain flexibility, certain stiffness, you will have each point moving by itself, and you have an infinite number of such points, which means an infinite number of degrees of freedom. So similarly, the natural frequencies also, in a n degree of freedom system, you will have only n natural frequencies, but here you can have infinite number of natural frequencies, but not all of them are important. It's only the first few natural frequencies which are important. And you would have different frequencies in bending this way, another natural frequency bending this way, another natural frequency in torsion, another natural frequency in axial loading, etc. But all of them will have certain values, and then for the same bending you can have a second natural frequency which is at a higher frequency than the first natural frequency, etc. One of the important natural frequencies that we will keep encountering in our structural analysis is the first bending natural frequency in this particular direction, which is essentially for the helicopter rotor blade, it's a flap. In the case of let's say a fixed wing aircraft, it is essentially due to the lift distribution. You would have the wing going up, bending up, but there could be gust or a vibration or turbulence, etc., because of which it might have a small vibration level this way, and if that turns out to be close to this natural frequency, then it can go through resonance, and slowly the vibration levels will increase, and there's a chance of the wing breaking off at the root. So to avoid that, we want to see that this, as this arrow suggests on the top over here, we want to keep the natural frequency as large as possible, so that none of the typical loads which arise, whether design loads or off design loads, will not be close to this. So in other words, we are interested in not only the value of this frequency, but trying to push this value as high as possible without causing a humongous weight penalty. So that's the purpose over here. Now, again, we are not going into the derivations of these. We are not at the stage where we can do that, but take it from me at this point in time that this natural frequency, the first natural bending frequency, is proportional to a few things, and one of that thing is 1 by L squared, where L is this length that we are talking about. So the more the length, you see that there's inverse proportionality over there, and the frequency is going to come down, which we don't want. We want it to be as large as possible, but we don't, as structural engineers, have any say over what the span has to be. It's typically given to us by the aerodynamic designer. They specify the span for us, so we don't have too much of a play around this L. On the other hand, there's another quantity to which this omega is proportional, and that is the Young's modulus of the material. Here, of course, we have multiple materials. We'll come to that shortly. But Young's modulus times the moment of inertia which we introduced over here. But we said that this is typically what is known as a bending stiffness. So the bending stiffness is typically a material property into a geometric property, and this is a very important thing to note, because all other stiffnesses also, we shall see shortly, will have this kind of a form, that there will be a product of two quantities. The first quantity will typically be a material property, and the second property will be typically a geometric property. So we have two things to play around with by either changing the material or the material distribution, and the other way of doing it is by increasing or decreasing certain shape and size parameters, so that we can control I as well. If we want to keep this high, we want to keep EI as large as possible. If you have already chosen the material which gives us the largest E, which we can still afford for this particular application, then our next opportunity is in terms of maximizing your I, so that we can keep the overall EI large, and therefore omega large, and therefore avoid resonances, and similarly in terms of static loads you can reduce the deformations as well. So other than EI, there's also in the denominator factor M, and this is something that you will see typically in all natural frequency problems. You might be familiar with the spring mass damper system, you have gone through. So this natural frequency there, you remember the formula for that? The first natural frequency in terms of the spring constant K and the mass M of the, excellent, yeah. So it is square root of K by M. So you see a similar dependence over here. This is half is square root anyway, and so you have an M in the bottom, and the K, or the stiffness that you see, is instead of the spring stiffness, you now have the bending stiffness of the beam that you have here. So it is following that similar square root of K by M over here as well. So anyway, so that's as far as natural frequency alone is concerned, but I'm not in having the luxury of deciding everything based on that, because I also have I'm designing for aerospace, so it's a weight sensitive design. So I have to somehow bring these two together in order to make up my decision. So that's what we will do next, to combine these two. It's not an equation, it's a proportionality, but essentially we're trying to get to omega being proportional to certain quantities on which I can make a decision. I already told you L we cannot make too much of a decision over, but because the aerodynamicist does that for us. But H is the overall thickness of this entire sandwich. T, remember, is the thickness of the face sheets, but H is the overall thickness of the entire sandwich. Now I have control over that. Of course, the bottom and the top might be sandwich configurations like this, and the overall thickness, again the aerodynamicist might between the distance between the topmost of this and the bottommost of the lower part of the wing skin, that might be decided by the aerodynamicist, because they are looking at the airfoil shape, the chord, and the total thickness, etc. But within that, how much material I can have and how much of hollow space I can have, I can decide how much of thickness I have. So H is something that I can play around with. Similarly, on this we are separating because we are dividing these two equations, and then we are showcasing that we are having this in terms of purely material. Should have highlighted E also in blue. This E also should be highlighted in blue because I'm highlighting all material properties in blue. So E by rho with the square root. So that is what is the material property of interest from purely from a stiffness based design point of view. The geometric properties are getting into this. So for a given geometry, which means that H by L gets fixed. So L is fixed, H is also fixed. Now if I'm playing around only with the material, then you see that the property of interest for us is the square root of E by rho. So E by rho power half, which is the material performance index, very similar to sigma U by rho that we had earlier for the strength. Here we are looking at the square root of E by rho. Many people would just give it as the specific stiffness E by rho, which is good enough, especially when you're looking, your focus is only on statics and only the deformation control is what you're looking at. But especially when you're looking at dynamics and looking at forcing your natural frequencies to be as large as possible, then the square root also becomes important, because two quantities, one might be very large compared to the other, but once you take the square root, they may not be as large compared to each other. So which means that it is much more sensitive than we think, which is why this power half is kind of important over here to keep in mind, especially for most structures which are subjected to dynamic loads, and therefore their natural frequencies are of interest to us. Is this clear? So let's now get head on to the third, or before that just a question. Oh, I should have removed this, but anyway. Now this is a question I typically ask some of my students. Which of these situations that I have listed over here are typically situations where there could be a compressive load and therefore there is a possibility of instability? Because remember, I talked to you about, we are discussing three types of designs: strength based, stiffness based, stability based. Last class we already finished strength based. The early part of today's class we already finished stiffness based. Now we are heading towards stability based. And stability, one of the things in elastic stability is the buckling that we are familiar with. So now before we head on to buckling, we know that buckling typically happens in these civilian columns, for example building columns, is in terms of the compressive load, and therefore there is a possibility of it kinking in flexure, and therefore that is what we typically call as buckling. So everybody knows that there is going to be buckling when you are going to have a compressive load, but is there a possibility of having compressive load and therefore a possibility of instability or buckling under these other kinds of loading conditions is what we would like to explore here. Okay, if the load is sufficiently large, of course, because if the load, even the compressive load, if it's very small, you know that this is not going to buckle. Once I increase it beyond a certain critical value, what I call as the Euler buckling load, it is going to buckle either by bending or some other means. But is it possible that it can have a buckling, first of all compression, and therefore buckling under any of these other conditions? This is a giveaway. It is always true, right? So everybody knows this. What about, let's take one by one, a panel in pure shear, which means that what we are looking at is we are taking a thin panel like this, right, and we are subjecting it to a shear stress, right? So this is all that there is for this particular structure. It could be connected in whatever way, or it could be free and it could be loaded in all directions, doesn't matter. But essentially we are talking of this is on the, let's say, the X phase, and let's say this is the Y direction, so it's in the XY plane, and so therefore this is on the in the Y direction, so tau XY, and this is at tau YX. The way I've plotted them, of course, is negative, but I'm saying that that is the only non-zero stress acting on a particular structure. So it's a panel, as you can see. Panel means that the thickness or height h is small compared to the other dimensions of L and B, length and breadth. So therefore it qualifies as a panel, right? And the fact that this is the only load means that it is under pure shear, right? So under such a situation, can the structure buckle is the question. Any takers? Yeah.
So, like, since there's two different like shear going in two different directions, there is a possibility that the panel might twist in a certain way, but I'm not sure if that counts as buckling.
Okay.
Because with buckling, it has to be under compression.
Correct.
So I don't think it would buckle if it's on it would for shear.
Okay, okay. That's a reasonable first take. Anybody else would like to take a shot on this? You've done the course on deformable bodies, right? So have you gone through Moore's circle in that? Yeah? Stress transformations, Moore's circle?
It's been a while for me.
Yeah, I know. That's okay. So what that essentially says is that even though in the xy coordinate system this might look like a pure shear, if I take at a certain angle towards this, there can be a possibility of other kinds of loads. To understand that better, let's take just a small square infinitesimal element over here, and let me draw that separately over here. So now I'm just taking a small element and putting it here. So this is in the x and y directions, that is fine, right? So in the x and y directions, it's very clear that it is still what we talk about here, the adjective pure is still valid, that it is a pure shear. But if I want to transform this, you would see that if, for example, I take at an angle 45 degrees to this, and therefore I plot on an element like this, you see that the resultant of these two and these two is such that it is stretching in this particular direction. So in other words, this will result in a stretching in this particular direction. On the other hand, if I look at it from this perspective, it see that it's getting pulled in. So which means that it is possible that it's getting compressed like this. It's not possible, it is in fact happening, right? So in other words, and these are going to be related to your tau xy, which is why I asked you about the Moore's circle. Typically the Moore's circle is plotted tau xy versus sigma, okay, and then you would see that this typically will have depending upon the kind of problem that you have. In this case it's a pure shear, so you would have the circle which is centered at the origin 0, 0, and this is your plus tau xy and minus tau xy, and because both these points are on the y axis, you see that the sigma stress is equal to 0. So in other words, there is no normal stress. Now that's this particular configuration that we are looking at, okay. So on two perpendicular directions you have plus tau xy and minus tau xy which are operating, and then you have 0 values for the sigma. But if you take at 45 degrees away, which means in a Moore circle, you will have to move double that angle. So here you are moving by, so from going from here to here, we are moving by 45 degrees. Here we are moving by 90 degrees. So when we move by 90 degrees, the points that we reach are this, and that's precisely what I have shown here, that these compressive load and tensile load, and because it is a circle of a constant radius, it means that the radius here is tau xy in magnitude, and therefore this stress sigma is going to be equal in magnitude to your tau xy, and this sigma is also going to be minus tau xy because it's on the negative x-axis, right? So which is what we have shown over here as a possibility of tension in one direction and compression in other direction. So very much it's a possibility that even when you have something subjected to pure shear, it is going to buckle. And this is one of the main reasons why you see buckling and post buckling happening in the wing skins, the fuselage skins, and also the webs of the spars, which are all subjected purely to shear, predominantly, or shear is the dominant load. Other loads are very small. In such situations also there is a possibility that in certain other directions it can buckle. So we have to be careful to design for avoiding buckling in other situations where it may not be obvious to us that there is a compression, but if you just do a stress transformation, you would see that there is compression in certain other directions. And this is for a special case where there is pure shear. If it was a different kind of a problem, in general this Morse circle could have not been centered at 0, 0, it could be centered at some other point on the x-axis somewhere over here, but still you know that there is a possibility of a compression happening over there in addition to certain other loads, which is the tension or whatever. So but you can see that there are possibilities there over there, but as you move towards the right, you see that both of these will become tension. So then there is no possibility of a buckling happening, but it's a possibility that the Morse circle moves on this side, then you see it's even more of a possibility that there is buckling. So always make sure that you test in other directions as well before you conclude that whether I should test this for buckling or not, whether I should test this for stability or not. Okay. The reason why I am going through this particular exercise is that people think, yes, strength based design is very important because I don't want my material to fail. The stiffness based design is important because I do not want resonance, one. The other is I do not want the deflections to be too large and therefore completely change the aerodynamic configuration or even touch the ground, for example. So I don't want that kind of a situation. So you see that the importance of strength and stiffness for most problems, but very few people see the importance of stability, and which is why you see in many textbooks also, unlike Baushaw and Craig's textbook, most other textbooks will kind of ignore this stability based design quite a bit because they say it's only for columns. But it's not only for columns, but there are many other cases as well where you could probably encounter this situation. I'll leave it up to you to explore these other options. Would you like to consider any one of them specifically? If you're interested, we can go through that. Yeah.
What if you just look at anything in a different way, you could probably see there being some sort of compressive element being on the material.
Yeah,
so
yeah.
All of these different forces?
It wouldn't be, right? So this example that we considered over here, there's no compression because it's moved to the right side of the to the right side, so it's not having any portion on the negative x-axis. It's only in the negative x-axis you have compression. Positive x-axis you don't have compression, right? So there are certain problems where compression may not occur at all. So this kind of a load, let's take this example over here. What you have is essentially you have that shear, along with you have a particular tension acting at the same location, right? So this is, let me call it sigma naught. So then what I'm having in this particular example is, in addition to a tau xy, I'm having a large value of sigma naught, which is tensile, right? So you see that. So that this value of sigma and this sigma, you see. So that's what I have. So if I transform here, the Morse circle gives you all the directions from 0 to 45 to 90 to back to 180 degrees. So it's giving you the entire spectrum, all directions. So when you're having all directions, you see that nowhere is any point on this circle having a negative value of sigma, right? So there are some exceptional cases like this, yes, where stability is not at all of consequence, but you should always check it out. More circle is just a geometric way of checking it out. There are also numerical ways of checking it out using the stress transformation equations, which is essentially in terms of cosines and sines of that angle theta. You will be able to arrive at expressions for that, and you can plot versus theta, and you will see where it goes, if at all it goes, does it go to negative value, and if it's a negative value, is it large enough to be of concern or not, right? So this is an example where we are talking about not only plane shear. So going back, tracing back this over here, what I'm saying is I'm going to have a tensile load this direction. So this tensile load is kind of dominating, and therefore this shear load is, even though it causes compression in the other direction, when it adds up to that tension, it becomes nullified, or it becomes still remains tension. So there's no compression at all. Yeah. So this is something again probably a few people are confused about, because torsion, there is also a possibility of buckling happening, because torsion, when you are applying torsion, essentially the way the material reacts or responds to it is through shear. And so essentially we come back to this kind of a problem, and therefore there is a possibility in a certain other direction you will have compression, right? So that's how it goes, and you can actually look through the other things, because the other things are involving bending, and whenever there is a bending, for example, you know that when I bend this, the top is going to be under tension, the bottom is going to be under compression. So compression is an issue, and therefore you should avoid local buckling. The beam as a whole may not buckle because it's under pure bending, but the bottom skin or the bottom surfaces or the bottom, even the stiffeners, if it is not designed well, they can all buckle, and so you need to make sure that that is taken care of. Yeah, so that having said, the motivation for stability beyond columns alone, that stability is important for other cases as well, other kinds of structures, other kinds of loads as well. So therefore we will take this example over here, and now we will consider, instead of a beam or a sandwich like we did in the previous example, two examples, here we will look at a simply supported plate. All four edges are simply supported, and just two of the edges there is a compressive load acting, and you know that any other situation can be brought to an equivalent kind of a situation but some other direction. So now this is a sheet of, it could be a metal sheet, it could be a laminate, whatever, but it's of thickness H, and the boundary conditions are that it is simply supported. The BC stands for boundary condition, SS stands for simply supported, which is what we have marked on all the edges, SS referring to the fact that it is simply supported. Once again, we are using the same notation for the breadth B, the height is H, and the length is L. Now the criterion in the previous two cases was avoid material failure, avoid deflections, or increase the natural frequency beyond a certain level. Now here what is the criterion? We want to avoid a failure in elastic stability, which we call buckling, but it could have various connotations like wrinkling, local buckling, crippling, etc. They are all subtly different from each other. We will encounter them as and when we reach there, but right now essentially we are trying to avoid buckling, right? Now what is this in terms of the loading? What do we have? We have an in plane, that means within the plane of the plate we are having a compressive load, which we are denoting by P, and this P, if you go on increasing, there will be a certain value of P which will be called as a critical value or a buckling load, beyond which you will see that this will bend. Even though we are not applying any bending load, it is possible that it will bend. Why does it happen? One is a possibility because there is a geometric imperfection or a material imperfection which will make it not as symmetric as it looks, because ideal case, purely from a mathematical point of view, if we see it as purely symmetric about the mid surface, the top and the bottom, there is no reason why it should buckle upwards or downwards, right? when I'm trying to push it this way, why should it buckle either upwards or downwards? It is going to do either one of these, but why should it have a preference? It is the same from a purely mathematical idealized point of view. But in reality, what happens is that there's no such thing as perfect symmetry. There might be a little bit of asymmetry on the top and the bottom, either from a geometry point of view and or a material point of view, because of which there might be a tendency to go one way more than the other. Even if it is slightly more, it will take that path, because that is typically how nature works. And all engineering materials also coming out of nature typically work, that they have a tendency to move towards the least resistance, and that's how the direction in which it would buckle. So, and that buckling load, again, you'll have, just like the frequency in the previous slide I gave you, and you had to trust me until we reach there. Here also I'm saying that trust me until we actually derive this, that PCR is proportional to certain parameters which define this structure. One is the Young's modulus of the material that this is made out of. The other is the thickness, overall thickness H of this sheet, and that cube actually, and divided by the breadth B. Okay, so this is how these parameters are going to affect it. Now, once again, it's a weight sensitive design because it's aerospace. So therefore, we bring in the mass of the this entire structure as well. It's a cuboid, very simple, density into the volume. Volume is breadth into height into length. So that's what it is. Now between these two, I know that H is also a parameter I can play around with. So let me eliminate that, because I'm interested purely in getting to the material parameter of interest to avoid stability. So let me eliminate H, which is a design parameter, just like the choice of the material is. So therefore, when we do that, between these two, if I, for example, from this, I substitute H as m by rho BL into that, and reorganize the terms, I can put together separately a material term over here. That material term is in the second bracket over here, and it is E by rho cube. Whereas the first bracket involves the mass, which means that what is the mass that I am allocating for this structural component, which in turn depends on the overall 20 to 25% that has been allocated to structural weight for the overall aircraft. From that various components, I am redistributing as a structural engineer how much percentage I want to give to each one of them. So I know the maximum mass that I am allowing for that. So that is one thing that I have. The lesser the better, but I have a peak on that, or an upper limit on that. Now, as far as B and L are concerned, typically it is dictated by the, if it's for the entire structure, but if it is for individual panels which are going to join, I am going to join to each other in some way, then I do have a choice over the B's and L's as well. But it's a geometric choice, it's not a material choice. The material choice is essentially coming from this E by rho cube, and that's what I'm trying to extract out of this simple exercise, that for a given mass, and that is M, for a given geometry B and L, the material property of interest which is going to either increase or decrease PCR is this E by rho cube, right? So I want to increase PCR because I want to keep my critical load as large as possible, so that the actual load when I'm applying, I have much more leeway in how large a load I can apply. I don't reach PCR by that time, so which is why we would want E by rho cube to be as large as possible. And this cube is a very, very important thing to look at over here. Unlike in the previous examples where we had a square root of E by rho, there was a rho, but it was appearing as rho power half in the denominator. In the one before that, in the strength based design, it was appearing as sigma U by rho power 1 in the denominator. But here it is a very, very large factor that is there. In other words, this is the most weight sensitive criteria. Stability criteria is the most weight sensitive criteria. Next is strength based, next is your stability based. Right. So your from a purely material point of view, we can conclude that your PCR is proportional to E by rho cube, and which is therefore the material performance index that we were looking for from a stability based design perspective. Typically, as I said, most structures will need to be have a consideration for all three of these, and therefore we'll compare, and then we will decide which material suits a particular application the best amongst the pool of materials that we have access to for a particular structural application. Is this clear for the stability based design? Do you have any questions on this? Yeah, smooth. Okay, so now let's look at some examples, because we were looking at steel as one of the candidate materials before we went on to look at titanium alloys and aluminum alloys, and we have not yet introduced composites, so to speak, in terms of the material properties, but we were just comparing those three. But it's important to note that steel is not, even though I gave single values for sigma u, for E, for rho, etc., steel is a huge family, as you all know, and the tensile stresses, strengths that you can see, such a wide range that it has, all the way from here 200 to 2000, as one order of magnitude over there. That is the kind of stretch that you have, and this is the elongation percentage at failure, what strain, normal strain it can take before it gives up. So that elongation percentage also can be as low as less than 1% or so, all the way up to close to 80%. And all this in terms of the differences that you see, different kinds of generations of steel, the way they are made, the kind of alloying elements that are there in addition to iron, which is typically the dominant element in all of these, which is why it's called steel. But in the additional metals that go into it, and also the heat treatments that go into making of these steels, all of that are going to give you that huge spread. And there are some which are, for example, we looked at two criteria, strength based design, stiffness based design. There might be an application where strength is more important than stiffness. So then I would rather prefer something like this, even though its elongation percentage, I'm sorry, I would probably be okay with a large elongation percentage as long as it is able to give me larger strength. But the other way around, I might want some materials which are very low in elongation as well. But there are materials like these are giving you not only low elongation percentage but also large tensile strength. But there can be certain applications where you want to get into the plastic regime. For example, those materials which are going to be taking bird hits, or it's going to be taking other kinds of impact, like even the undercarriage, which is usually made out of steel. You want a lot of energy absorption. You want the elongation to be large. You do not want elongation to be small, because the larger the elongation at the emergency kind of situations, large loads, you would want it to absorb more energy so that it doesn't transmit that energy from the ground through the undercarriage to the cockpit and the cabin, which could be disastrous. The whole idea is it should be able to deform in such a way, maybe even take up damage, plastic deformations, permanent damage, permanent deformations, so that it takes up most of the energy and doesn't transfer the impact energy to where it matters, namely the cabin and other electronics and the passengers and the pilot, etc. So that's essentially. So it's not that the larger or smaller value is not like an absolute thing that it's always good. Okay, so you'll have to make a case by case judgment depending upon the specific applications at hand. Is this clear? Okay, now we'll bring in our what is the current state, and it also in terms of what is going to be probably the future, is that in addition to the three that we were already talking about, the three metals or metallic alloys, we are now bringing out these composites at the bottom of this chart. And now we have, I'm sorry about that, that should be sigma u over here. So sigma u is the sigma u by rho is of course the strength based criteria. This is the stability based criteria, is square root of E by rho, and E by rho cube, which we just now derived, which is the stability, this is the stability based and this is the stiffness based, right? So based on the natural frequency we had derived this. Now if you look at the comparison over there, then you see that there's hardly any comparison between these. They're almost fairly close to each other, and of course each of them have a fairly large range in which for a given kind of material, steel. There are so many steels as we saw in the previous slide. I'm not even taking all of them into account, but the typical ones which are used in aerospace, if you look at that, that itself has a fairly large range to be considered. So we cannot make a statement just that steel is bad for this or good for this. Which particular steel are we referring to, and have we looked at, exhausted the other potential candidates amongst the steels itself, etc. we have to take a look at. But even if you look at the maximum of each one of these are fairly low compared to the composites that we have over here. These also will have a range. It doesn't mean these are specific values that I have given, but these are kind of ballpark values typically used in aerospace industry. Within each of these categories, for example, many different types of carbon fibers, etc. are there. And here /EP refers to the epoxy resin, which is most commonly used, or which was being most commonly used in aerospace. But slowly there has been a movement from these so-called thermoset resins to thermoplastic resins, which are much more environmentally friendly compared to all of the thermoset matrices, including epoxy, and therefore there's a tendency to move towards thermoplastics. There are other advantages also, but the disadvantage is that the manufacturing processes are a little more complex compared to what it was with epoxy, and therefore, but most of the aerospace industry is moving away from thermoset matrices like epoxy, reducing their content and slowly increasing the content of thermoplastic matrices. But this is what is mostly used. There can be metal matrix composites, where instead of a polymer like this, you are having a metal as the matrix, in this case boron aluminum. So boron is the fiber. Even though we say boron fiber, it's actually a boron fiber. It's actually a carbon fiber with boron coating that is typically there, which we call as the boron. So it's typically much larger fiber diameters compared to most other E-glass, S-glass and carbon fibers. This is typically used as a fiber in metal matrix composites. When do we use metal matrix composites as opposed to polymer matrix composites? Typically for higher temperature applications, because polymers cannot take very large temperatures. So when you're, for example, designing a structure closer to the engine, it may not be at the combustion chamber or the turbine where it is too hot, even for metal matrix, many of these metal matrix composites, but if it's closer to the engine or in the engine exhaust region, etc., you might as well go for this. These are slightly heavier compared to the others, but still in terms of what the parameters, the specific parameters that we are interested, the strength also goes up so much that even though the density goes up, the ratio of the strength to density is still comparable or even better than some of the carbon epoxies, for example. Similarly, so again, there's a distinction between carbon and graphite. So typically graphite, even though that's also a carbon, it's a particular kind of carbon, you still have in terms of the nomenclature which is typically used in the composites industry, not just aerospace, is when the percentage, the purity of the carbon is larger, you typically end up with graphite, and therefore you have a certain range that you see over here. For example, this is the stiffness is much larger in graphite compared to carbon. So even though both are carbon, this is more pure carbon you are heading towards, therefore you have larger stiffness, but the strength might actually be lesser. So again, you have to make a trade away between these different properties and their relative values, depending upon the specific application, where you know whether failure is more important or a critical demand over there, avoiding failure that is, or is it to reduce the deformation and to increase the natural frequencies, is that the dominant demand over there for that particular component. So based on that we typically make the choice. Sometimes there's also a way in which you can mathematically bring in a weighted average of this. You give a certain weightage for this, certain weightage for this, and you consider both and eventually make a decision based on that combined compound value that you have. So that these are things that are done typically in each industry in a different way. Each industrial member like Airbus might do it in a different way, Boeing might do it in a different way. Most of these are confidential and not revealed, but essentially you can see the process at play. And then of course the final criteria is the stability criteria, which is important in most cases but not all. But there you see the humongous difference between composites as a family and the metals, and this is where you see there's a huge win that happens in terms of because of the rho cube in the denominator. The dominance of the density makes the composites much more better candidates wherever stability and avoiding buckling, that is, become critical. Okay, so in terms of, I think the black what is marked is within the metals what is the best. So compared to 0.5, around 0.1, 3.7 is the best, which is why you see aluminum alloys doing so. We use so much of aluminum alloys in a lot of aerospace applications. Until composites came, they were probably almost entirely made out of aluminum alloys for a large class of aircraft, but now it's kind of shifting towards the composites. Similarly, if you look at purely from a failure point of view, you would see that steel might be better than the other metals. So which is why where failure is the important criterion, like the landing gear, etc., you would typically still continue to choose steel, even though you would have rho very large for that particular thing. Sigma u by rho is still something which is kind of helps you to make a choice over there. But once you go towards this and see that these are also important, then the shift happens in terms of the choice that you're going to make. Is this clear? Any doubts or questions on this slide? Okay, so next let's look at composites. So I think the previous slide was good enough if you already didn't have enough idea in terms of why composites are so important. Purely from a mathematical and numerical point of view, we try to compare and say that make a case for composites, and therefore it's important from a structural analysis point of view to have an understanding of these composites. To some extent you already have had a materials course in which you have been introduced, but there are certain features of specific relevance to this structural analysis, which is what our focus on the composites will be. We'll have a very brief introduction to them. Okay, so this will be more in terms of answering certain questions. To some extent the first question is kind of answered by the previous the slide before the last, which was why first of all composites, and then what are these composites, how are they different for example from alloys, which are also mixtures in some sense, but it's a mixture at a different length scale. So what are these composites is what we will look at, and where they are used specifically in the aerospace industry, which particular components are made, which is again going to go back to your exercise that you had, the assignment in which you presented the various materials in some of the aircraft like the ALH and the NAL aircraft like Saras, Hansa, etc. When you made the presentation on that, you saw that there are certain locations where certain composites are preferred, certain locations where instead of composites you had metals, within composites where glass fiber, where carbon fiber, etc. Some of these decisions we will look at when we look at where, and finally we will look at how, in the sense that from a structural analysis point of view, that's where the core of this course is, in terms of how do we handle, if a structure is made out of composites, how do we handle that analysis, and how all other analysis made out of structures made out of other materials like metals can be thought of as a subset as long as failure has not been reached. Once failure has been reached, metal becomes a very complex animal to deal with because it gets into the plastic regime, etc. Whereas in the case of the polymer based composites, you will have no plastic regime, it will be a brittle fracture, and so things are done and dusted. Once the material fails, it is sharp failure for you. So that's what we are getting into. So this how part is your major chunk of the structural analysis course, but in order to get there, we'll very briefly answer the first three questions. So why, of course, very clearly there are merits compared to the conventional materials. By conventional materials we are referring to aluminum alloys, to some extent steels and titanium alloys. Compared to them, we saw sigma u by rho, square root of E by rho, and E by rho cube in particular are very large, and therefore that is the merit. That is purely from these three criteria point of view, but there are other merits as well, and we will briefly go through them as well. Now, as far as the second question is, what are composites? Essentially, they have two major constituents, the fibers and the matrices, with very clearly observable interfaces between them, unlike in the case of let's say metal or metallic alloy rather, where even though you have multiple metals in the metallic alloy, they are at a much lower length scale and there are not very clear interfaces between them at the level of length scales that we are interested in, and therefore that's one of the major differences. But these are not the only two constituents. There will be quite a few additives depending upon the specific applications. Now, next is, where do we use these composites? So we will look at a few typical applications, and then how composites are to be analyzed. That is essentially the structural analysis or structural design and the mechanics which goes into modeling the mathematical models for these not only materials but also the structures made out of those materials. Okay, so this is typically how you would have fibers in a particular direction, which is different from the structural directions, because you know probably a priori from the design estimates that the loads are going to be dominantly in this particular direction, then you want to put more fibers in this direction. But typically you will have under different phases of flight loads coming in different directions. It's sometimes perpendicular to this as well, in which case you will put multiple layers and you will put fibers in the other direction as well. So that's how the decision is made in terms of how you design a laminate out of a composite. So, but let's answer these questions one by one. The first question that we asked was, why use composites, right? And before we get into why use composites, any choice have its advantages and disadvantages. So we'll first list out the disadvantages and see what is the issue when we introduce composites. So that's why I say, why use composites in spite of these facts. What is the first fact that is of consideration over here? It's a very, very complex material characterization. You will get a taste of it as we get into it, that it is much more difficult to do structural analysis with a composite structure than it is with a metallic structure, at least until the point of failure. So the material characterization is complex, and the complexity is primarily due to two reasons. One is anisotropy, that is properties are different in different directions. The other is heterogeneity, that properties are different from one point to another point, both of which make this fairly difficult to deal with. The second thing, and the complexity is not only in terms of the theoretical analysis that we are going to do and theoretical design, but also when experiments are done to test or to validate these theories or to verify, then you will see that once again the experiments with composites are a little more tricky than those with metals, and that's another thing to be aware of. Then what does this have in terms of an implication? Just because something is complex, we are not going to be shying out of it, because we love challenges, we want to take up challenges, right? But there is, from an industry point of view, these complexities are going to have some kind of a penalty. What is that penalty? It's going to, because it's complex characterization, your design times are going to go up, and therefore the cost in terms of how many people you are going to put on to work on that, and how many computers are going to be engaged for how long, all of that goes up, and therefore the overall cost goes up. So both the design time and the design cost in terms of dollars will both go up, and therefore the complex material characterization is an issue. But we will see, these are all problems, but we still use composites obviously, because their advantages are of much more value to us than their disadvantages. The second thing that you should be aware of when you're designing structures, aerospace structures in particular, with composites, is that they are much more susceptible to impact. So impact damage, when you have an impact damage, in the case of a metal, this energy absorption characteristics are much easier to understand, whereas because it can enter into even a plastic regime. But here most of these polymer based composites are all brittle, and it's going to break, and some of these breakages might initiate not on the surface but somewhere in between, because remember we are using laminates which are layered structures, and an inner layer might fail before an outer layer, and therefore the damage may not be visible. So through visible inspections you will not be able to determine it, and it might be a little too late if you have not employed any other non-destructive evaluation techniques, etc., for you to detect, and it could be quite dangerous. So that's why impact susceptibility is something we should be aware of. The third thing is compared to metals, which can, for example, iron can rust, but having steel prepared in a particular way, you can avoid rust and things like that. So metals have been around for so long that the effect of moisture has been taken into account to a large extent, at least the aerospace grade metals that we are concerned with. On the other hand, even the aerospace grade composites, there is a possibility when you're operating in high humidity areas, let's say amphibious aircraft or aircraft which are taking off and landing on naval carriers, large ships on which the aircrafts are landing, aircraft carriers that is. So there you would see that it's not only moisture but also salt water, which can cause other kinds of issues as well. One is the moisture can get into it, and there can be a swelling of the polymers into which these fibers are embedded, and therefore these swollen composites can have inferior properties compared to the original composite that you are designing the structure with. So that's something to be aware of, the moisture issues. So it picks up the moisture much more easily than a metal would. The next thing is in terms of recycling issues. As I was mentioning, almost all composite structures in aerospace industry till recently were being made mostly out of epoxy matrices, and these are thermoset matrices, which means these plastics, one set are done. You cannot do anything about it once the life cycle of the aircraft or the aircraft structural component is done. You cannot kind of recycle it in any way, which means it's an environmental disaster. But now, as I said, since we are moving towards thermoplastics, this is to a large extent something that we can deal with. Next is, you can see in this particular slide graph over here, we are plotting the Young's modulus in any arbitrary direction x as a ratio with respect non-dimensionalized with respect to the transverse modulus. That is the modulus perpendicular to the fiber direction. So E1 is along the fiber direction, E2 is perpendicular to the fiber direction. Now you know that along the fiber direction the properties are very superior. In other words, the Young's modulus is very large compared to the Young's modulus in the perpendicular direction. But anywhere in between, it's having an in-between value. So here, for example, you see that your Ex by E2, which has a maximum when x becomes one direction, that is the fiber direction, you see it can go as large as 14. So in other words, your E1 by E2 can be as large as 14 over here, which is the case for the carbon epoxy over here. Of course, the other end of the spectrum, it has to come to 1, because that's what you're non-dimensionalizing with respect to. You're dividing everything by E2. So you see that everything is becoming asymptotic to Ex by E2 equal to 1, because it becomes E2 by E2, which is 1 at the right end of this graph. So now if you see over here, this is plotting versus the fiber angle with respect to the x-axis, starting from 0 to 90, and in many cases you're seeing that the drop is drastic. It's not that this region is very poor in stiffness, but even if you go up to about 45 degrees, you see that it is fairly low compared to what you have over here. So in other words, the drop happens within about 20 degrees or so, depending upon the specific composite, of course, and the drop is quite severe, especially for the high performance composites like carbon epoxy, and therefore we have to be very much aware of this. So remember that everything that we are listing in this slide is the in spite of. In other words, the disadvantages of using composites, because even before we set into its advantages, we should be aware of its issues and how to overcome. So each one of them, while introducing them, I have talked about the solution for that. Here of course better and better mathematical models which can handle these complexities quite efficiently today. Here in terms of the impact susceptibility, using multiple materials and combinations thereof, and maybe even going to metal matrix composites. And within composites there are certain fibers like Kevlar, for example, which is a DuPont trademark for aramid fibers. The chemical name is aramid. Those are very good at taking impact. So it's you cannot use carbon fiber or glass fiber for everything. You should make sure that you use the appropriate fiber like aramids, that is Kevlar, for regions where bird impact or other kinds of impact, tool impact, etc. are probably much more, so that you have to take care of. Similarly, moisture pickup, the way you make it waterproof through certain additives, etc. There are many other ways in which this can be handled as well. Similarly, recycling issues, we saw thermoplastics can be used instead of thermosets, so there is a way of overcoming that. Now we are talking of poor transverse properties. How do we overcome that? By not having fibers all in one direction. It's like not putting all the eggs in one basket, but you're having fibers in multiple directions, so that all directions in which loads can be anticipated in design and off design conditions, you have enough stiffening or reinforcements for that purpose. So that's how we take care of the poor transverse properties. But poor transverse is not the only thing, it's also poor shear properties. Poor transverse properties, poor shear properties. So it's bad in shear, and that's where the sandwich kind of construction that we talked about, where we introduce a foam or a honeycomb in between, etc. So those can take care of that. So poor transverse and shear properties, and when you're talking of properties, we are talking of both the ultimate strengths, ultimate compressive strengths, ultimate shear strength, etc., and also the corresponding stiffness in these particular directions, the transverse direction, both tensile and compressive, that is perpendicular to the fiber. Similarly, the shear that happens, all these shear properties are going to be much lower compared to many of your metal structures. So you have to appropriately, and you know that from the Mohr circle that even though tension might be dominant load in one direction, it could become shear tension could be the dominant load in this particular example, but it could be shear in some other direction. So you have to be able to handle that as well. And we know this is poor in shear, so how do you go about doing that? So you would, for example, put fibers in the 45 degree, plus minus 45 degree, and or go for the sandwich kind of constructions where you introduce a core which is much better at taking shear loads, which is what we would try to do. Yes?
In like the previous table that weren't like the composites and stuff, didn't those have something like the highest stiffness and strength performance index factors?
This one?
Yes.
Yeah. What are you talking about?
Didn't composites, right? It seems like they all have very high strength and stiffness, performance.
Yeah. Yeah.
Indicators. But you say over there that it's very poor at handling.
Yeah. So all these properties are in the in the normal direction along the fibers.
Oh, okay.
So these properties that we are comparing are for a specific direction, which is along the fiber direction in tension. Again, even in compression, they may not be as good as this. Okay, most of them will be much poorer in compression as well. So whereas these guys are all the same in all directions, which is again a huge advantage you have over there. They might be low, but they are the same in all the directions. Okay, so here the ingenuity in terms of the design of the composite becomes very important. That's how the laminate design is done. The choice of the number of layers and the choice of the angles in each one of the layers, and the choice of which layer to go put on top and bottom, the order is also very important. So it's not just the combination, but also the permutation that becomes very important in this case. Yeah, a good point. So these are the things that we should be aware of, and the way we go around that is, as I said, using sandwich and or multiple layers with different fibers, different layers having different fiber directions. So that's what I say over here, overcome by using a proper laminate design. And also another issue with composites that we should be aware of, yes, when we buy, let's say, aluminum alloy, a particular kind of aluminum alloy, let's say AL2024-T3 or whatever. So now when we buy it and we try to make specimen from different portions of that lot that we have purchased, you would see more or less the same values for Young's modulus and or the tensile strength, etc. There might be a little bit of scatter, but if you do that with a composite and make specimens out of the same lot that you have got from the same manufacturer and make multiple specimens, you will see a lot more scatter. The properties that you get for sigma u, for E, etc., there can be quite a lot of variations, so you should be aware of that. Larger variations in properties between lots and also even sometimes within the same lot. So how do you handle that? So that's where one of the topics that I talked about in the very first class, the non-deterministic kind of modeling becomes important. So you start dealing with, instead of specific numbers for Young's modulus, strengths, sigma u, etc., you will have probability density distribution functions. How many cases is the value above this level and how many cases below this level, etc. So you'll have a mean, you'll have a standard deviation, and you'll start working with those models. Then it becomes much more easier to track and tractable for designing with composites. Right. Next, so we have seen all the issues, the problems up front, so that nobody will boomerang us with why are you using this crazy material. It has such issues, because we have seen, yes, we are aware of those issues, but we also know how to handle those issues, how to overcome those issues. Now we see the huge advantages of composites, some of which you are already familiar with. The first thing is the outstanding specific mechanical properties. Sorry for these font issues while going from the Mac to the iPad. So this is refers to sigma u by rho, the E by rho power half, and the E by rho cube that we derived for the three kinds of design. So all of these we saw in that table that we had very superior properties, as long as Nilesh brought out, you are focused on the fiber direction, but in any other direction you should know how to handle that. So next is in terms of the advantage of a composite is in terms of the tailorability. So when you're choosing a material for a design, if it's a metal that you have chosen, it's done and dusted. You have chosen the material. All that you can do after that is in terms of the sizes and shapes you can play around with. But in the case of a composite, even after choosing the specific fiber, the specific matrix for a particular composite, you can play around with the fiber directions, you can play around with the number of layers, you can play around with the angles in each layers and which layer goes up and down, jumbling them up. So all these flexibilities exist, and there are so many more variables that can help to optimize to the specific application. In other words, you're tailoring it or making it ready-made, not ready-made for multiple applications, but for a specific application you're tailoring the material as well. So in other words, in other cases, metallic structures, you're choosing the metal and all your tailoring is purely geometric. Whereas here, you're tailoring the material itself. In other words, you're designing the material for a specific component. Yes, it's the same fiber, it's the same matrix, but the volume fractions can be different, and all these laminate designs can be different, and therefore you still have so much play around not just the geometry, but even the material itself. The next is advantage of composites is that the ease of fabrication. Okay, so because it's available in various form factors and you can use it as it is. We already discussed in a previous class based on a question as to the autoclave, etc. But that's not the only way. There are other ways in which it is available. That is the most common way, the pre-pregs, where it is the fiber is in a pre-impregnated form in the matrix, and therefore you just take them from the storage, which is at a low temperature typically and still wet, and then you start putting it in the form of a laminate, then you eventually bake it. So those are typically when you have fairly long fibers, and very interestingly, what classifies as long fibers is anything which is greater than 10 mm, which is just 1 centimeter. You call it long fiber because the diameters are of the order of 10 microns or so. So compared to the 10 microns, 10 mm is fairly large, right? So it's about 1,000 times. So anything which is beyond a certain small value is a long fiber, and this is what your pre-pregs will be. So in other words, don't think that when you have a large sheet of pre-preg, all the fibers from end to end are all going in a 0-degree angle. There can be slight variations, and because they could be, it's not a single fiber which is going from length to length, unless it is a filament winding kind of a process where you're winding the filament itself, then you might have much longer fibers, but otherwise even this can be classified as a fairly long fiber, and it's pretty good at its performance. But then you have lower cost applications even within aerospace, for example, certain door kind of structures or a seat made out of a composite, etc., where these are not primary load bearing structures, but still it's important that they don't fail and they don't deform beyond a certain value. So then you use slightly less expensive composites, which means that you could go for what are known as SMCs, the sheet molding compounds, which are typically again of the same order, 1 inch kind of fibers that you have, but these are randomly oriented. It's unlike in the pre-pregs, even though you might have reasonably short fibers, about 1 centimeter, etc., but still you will, to the extent possible, you will try to orient them all in a particular direction in a given layer. So unlike that, in a sheet molding compound, you would have much more random distribution of the fibers, and therefore they are much easier to make and much less expensive to produce and sell. Then the third category is here you are talking of in two directions, a planar kind of thing, that is sheet molding composite, SMC, but in BMC it's a volumetric thing, and so it will be even shorter fibers and it will be even more randomly oriented. So the design tailorability is not that much like what you had, but the advantage is cost. These are typically used more in automobile kind of applications or other applications. Again, we are not talking of let's say racing cars like F1 cars, etc. They would have probably even superior composites than aerospace, but we are talking of the regular automobile industry or certain other construction industries, etc., where BMCs are used just for the economic advantage that they have. Then also in terms of the thermal expansion, you can kind of bring down, that is the advantage of a composites. We are again going back to the main bullet points. So you have an ability, because you are having polymer as the matrix, and the polymer matrix compared to metals will not have very large thermal coefficients of expansion. So therefore your thermal expansions will be lesser. In other words, due to just heat, you will not have very large variations in these shapes. So I'll just finish this slide. I think I'm done. Oh yeah, I'll just finish this slide and we will conclude today's class. So there are a few more advantages. So we already listed those. Those are the main advantages. In addition, we will have a few more advantages which might become the crucial, become the deal clinchers, so to speak, in certain specific applications. One is where you have very large dynamic loads and you need a lot of damping. So the material damping, because it's a polymer, it's fairly large, and therefore that is an advantage where you want to damp out vibrations, for example, and various other kinds of time varying loads that you would like to die down as quickly as possible, you would use that. The second is in terms of very large, so these arrows that I'm using over here refer to very large values, so moving upwards, so therefore very large values. So large value of material damping, large resistance to various things. So we saw it is susceptible to impact. Remember, that is an issue, but it is better than metals in handling some of these things like corrosion, for example. Metal is notorious for being corroded, especially in applications which are close to chemically harsh environments and or marine environments involving salt water, etc. So those kinds of corrosion issues are very, very less in the case of composites. But yes, moisture pickup is there. That is something you have to be concerned about, but it will not cause corrosion, it will cause material property degradation in a different way, and as I said, there are ways of overcoming moisture pickup, but corrosion is not an issue. Then the resistance to fatigue is also very, very high. In other words, which is again in some way related to the fact that it has very large material damping, and therefore its fatigue resistance is pretty large. In other words, cyclic loads which keep varying between large values of the load to smaller values. It could be tension and compression, or tension and tension but small and large, or compression and compression small and large, but essentially varying with respect to time cyclically. It will be able to handle many more cycles compared to a metal component of a similar category subjected to the same kind of load limits. The third thing that it is good at is resisting damage, because it has many different ways of getting damaged, unlike metals which are kind of boring in the sense the way they get damaged and how the damage grows, and of course they've been studied for so long that it's much better understood. But in composites you could have the fiber and the matrix debonding, you could have the fiber getting broken. If it's a compressive load, there could be a fiber micro buckling, that is individual fibers buckling at certain locations. You could have the matrix cracking, as I said. You could have between two layers the delamination occurring, and delamination could be because of transverse normal stresses that are called as peel stresses, or it could be because of transverse shear stresses. It could be edge delamination where the edge opens up, or it could be internal delamination. So various kinds are there, and one might lead to the other, and the way the damage grows is very interesting. For example, it's a matrix crack. This is a matrix rich region. There is a crack in this direction. The matrix crack keeps on growing very easily because matrix is not a very high performing material, but once it hits a fiber, then the crack stops growing, or it gets at least retarded or gets delayed in its growth, because it has to now go around the fiber. It cannot break the fiber easily, so it becomes a little more slower in growth. So there are many advantages like that. So damage, the slow crack growth, as I just explained, it's tailorable in terms of the fracture toughness. Like all other properties, we said it can be tailored, the strength, stiffness, etc. Similarly, your fracture and damage tolerance can also be tailored quite a bit depending upon the kind of dominant loads in a particular design, right? So then again, because of the fact that it is anisotropic, we can take advantage of that. We know the directions of the dominant loads, and therefore we can design for damages which can typically occur, and to avoid them or to at least delay them. And it's large for metal matrix composites. That's something that you have to bear in mind, because metal matrix composites to a large extent will behave like metals, because that is the matrix in which the fibers are embedded. The last thing that I would like to leave you with today's class is in terms of another advantage of composites is that not just mechanical properties but also the electrical and thermal resistance capabilities, because remember, metals are very good conductors of electricity as well as heat, and therefore they cannot offer much of a resistance. But in those areas where you want to avoid the environment's temperature conditions, or let's say a lightning strike, etc. How do you deal with? It's much more easier handled with the case of composites, because there are ways in which you can route these electric fields coming from a lightning, or the thermal flow coming from a certain thermal source that you have either in the environment or within the aircraft, which you want to kind of empty out to the environment. So all these tailoring is possible. Just as mechanical tailoring is possible, electrical and thermal tailoring is also possible. So these are all the advantages. So we have seen the disadvantages and we have seen the ways to overcome those disadvantages, but the advantages far outweigh the disadvantages, and that's why we are seeing more and more utility of composites in aerospace structures. And so we have kind of set up the motivation why composites. In the next class we will start in the beginning of the next class with why fibers and why matrices, what is the role they play, because that's very important in understanding, because using that only we will do the structural analysis. So when we do the structural analysis, we'll see what is the fiber doing and what is the matrix doing. So for us to understand that, we should first of all understand why we are using each of them, and then we will answer some of those other questions that we asked, like what, where, how, etc. And then we will get on to some of the equations governing structural analysis, which are valid universally, whether irrespective of whether you're dealing with composites or metallic structures, so that you have a common algorithm with which you can either design or analyze structures. Thank you.